Hi, good evening. Welcome to my daily live session on various topics for execution excellence. And again, today also, I'm sorry for having got delayed. Maybe the same thing will happen tomorrow also because tomorrow I'm traveling to a customer and it could get delayed. So please pardon me for that. I will, however, try to keep my daily schedule of trying to speak for some time in the evening. It's really quite inspiring and energizing for me too. And I've been talking about various methods and tools picked up random from my toolkit for execution excellence by changing mindset and culture on our quest and journey of creating world class companies and exceptional leaders. I've been, like I said, speaking on various tools and methods. And let me now give a very quick recap of what I spoke yesterday and then talk about a new tool today, which I had introduced to you yesterday, which is about capability studies. So, yesterday I spoke about Kaizen. And the most important thing which I said was when it comes to Kaizen, it's a mindset of wanting to discover and wanting to do something different, try out differently, experiment, be inquisitive. And that mindset is all about Kaizen. And improvement can be done in any area. And when you talk about improvement, it's important also to keep in mind what is the ideal state. So the improvement always is towards moving towards the ideal state. And that's what I had explained yesterday. So with that very brief recap, I'm sure you would be doing a lot of Kaizen in your lives. It can be done anywhere, at home, at work, on the way to work, wherever, even in sports, everywhere Kaizen can be done. So all the best with Kaizen. And coming back to today's tool, which I'll be introducing you to, is about the capability study. So what is a capability study? I think this slide, I need to make it a little bigger. So let me get back to the screen here and change the view so that you can see the slide a little bigger. Okay, so capability study. Now, I explained some time back about control charts. First, very brief background about nature and statistics. Anything which is physically measurable in this nature, anything, absolutely anything, any measurable, physical characteristic always follows a normal distribution. Normal distribution is something which is of the shape of the bell curve. That's why you see the bell here. Curve is, it looks like a bell. Therefore, it's called the bell curve or the normal distribution. Anything measurable. It could be weight of human beings. It could be the diameter of hair in human beings. It could be the thickness of leaves in a particular tree of a particular plant. You can't really take multiple plant trees and combine it together. Then it will also be normal distribution, but it would be basically collated. So it will not be a single normal distribution. There will be multiple nodes. It's called as a multiple nodes, and that indicates that there is a mixture of population. So anything which is measurable always follows a normal distribution. That is the first discovery. Then, if it follows a normal distribution, anything measurable coming from a system which is governed by some causes and it is working on its own, any system would generate whatever it generates, produces a normal distribution. Therefore, even processes, even machines would generate components which have dimensions in the form of a normal distribution. When I say normal distribution, the scale is very simple. You need to understand that the x-axis here is basically the diameter or the dimension that you are measuring, and the y-axis is the frequency of how many times it occurs. For example, if we look at the weight of a man, let us say the x bar is the mean value, that is the average. Let us say the average would be about for an Indian 5 feet 4 inches or 5 feet 5 inches. That would be the average. So the maximum number of people have that height, and then there would be less number of people as the height comes down. Let us say at 4 feet it will be very less, almost negligible, and similarly at maybe 7 feet it will be almost negligible. That's the way the distribution happens. The frequency gets distributed like a normal curve. That's why it's called as a normal distribution. That is the first principle, or first what should I say, fact which I am trying to share with you. This you can check it out by doing multiple studies. In fact, there are people who do a very simple study of pick up a ball and then throw it as far as you can and keep measuring the distance at which you threw, and that distance again for also normal distribution. Whatever you can physically measure arising out of a single system follows a normal distribution. First is that is something which you need to believe, because that's a fact. You can try it out, experiment for yourself, and then confirm that it is the case. It is the case because that is nature. And once that has been explained, I'm not really going to be what should I say, explaining the belief here. For any belief, if you want to understand how normal works, then I would be more than happy to. Uh, I'll be more than happy to come and talk to you. I don't know why Nagaraj can't see the slides. Are you able to see the slides now, Nagaraj? Okay, I am showing the slide already now. Capability study is what I'm talking about, and there is a slide with capability study. If you are not able to see, please again write back, Nagaraj. Otherwise, continue watching. And now I want to just add on to say that if you want to know more about normal distribution and how the standard normal distribution works, you are always welcome to write to me. You can write to me by sending me an email to dinakar@samutana.com, and I'll be more than happy to answer your questions and help you believe that there is nothing in this nature which is physically measurable arising from a system which doesn't follow a normal distribution. That's something which I can prove to you. So let's take the challenge, and you're most welcome to challenge me on that. Now, coming to the capability study. Before we get into the capability study, once it follows a normal distribution, then in any distribution, there are two main characters which are computed. One is called as the average, which is the mean of the population, or mean means average, or the central tendency is the other description for that, where all the values tend to fall. That is the central tendency. Then there is another attribute which is called a variance, or the how much does it vary, how is the range. Okay, these are the two characteristics which are computed. And for calculating the variance, or how much does it vary, how is the spread, one would calculate what is called as a standard deviation. A standard deviation is computed by the root mean square of the difference from the mean to the actual value, and then that is the standard average. Root mean square is the standard deviation. That is a formula. I don't think you need to worry about the formula. But what is important is to understand that depending on the standard deviation, let us say the standard deviation is plus minus mu is the symbol for central tendency. X bar, or what you see on the chart here, is the symbol for the sample average. See, the idea is, I spoke some time back about the watermelon concept, where before you buy a watermelon or a sweet, you pick up a sample, taste it out, and then decide on purchasing. Similarly, in all these natural occurrences, once you take a sample, you get the idea of the population. And the approximation of the population mean, which is denoted by mu, which you see at the bottom, is the X bar, or the average of that particular sample. Sample average could be is denoted as X bar. Sample median would be X followed by a tilde. Tilde is a sign in Portuguese. That is X median, or you could also use mode. There are three normal metrics which are used, but I would prefer X bar or median. Median is okay if you don't want to use a calculator. Otherwise, X bar is much better because you calculate the average. And so average is the approximation of the mu, which is the standard deviation, which is the central tendency of the population. Then you have the spread. Spread is computed in multiple ways. One is to calculate the range, which is the maximum minus minimum, which would give you the range of the sample. But you can't calculate the range of a population, because population, you don't know up to what point the maximum would be, what point the minimum would be, which means you have to check all the values in that particular population, which is being generated from a system. Therefore, it's quite humongous. So instead of that, what is done is you calculate what is called a standard deviation. Standard deviation is, again, like I said, root mean square average of the value deviation from the central tendency. That is denoted as S for the sample, and sigma for the population. So that's where the sigma comes in. Now I think the bell rang in your head. It is the 6 sigma comes from this sigma. This is 6 sigma. So when you talk about 6 sigma, it is 6 times the standard deviation on either side of the mean. If that is a total spread within the limits which you have got, then it is 6 sigma process. Now let me explain that, and that's where the capability study comes into picture. So now we have got the concept of standard deviation and the central tendency of the sample, which is standard deviation is S, and then central tendency is X bar of the sample. And similarly, standard deviation and mean of the mean central tendency of the population would be S sigma for standard deviation, and mu for the central tendency. There is another thing which is interesting to note, that the standard deviation is also, let us say this is more from a geometric perspective, is the distance where the inflection of the curve changes, the direction of the curve changes. If you see in the case of a bell, it normally has a curvature of this kind initially, and after that the curvature becomes in this fashion. The curve changes from this direction to this. That point where the direction of the curve changes is the point of inflection. The distance between the point of inflection and the central tendency, or the average, or the mean, is 1 standard deviation. That is also geometrically the number, so it's easy to understand. So that point of inflection to the central tendency, that distance is 1 sigma, or 1 standard deviation. So now comes the interesting part of it. That's where the basis is required for understanding the capability study. So if you take any natural phenomenon arising from any single system and you measure any physical characteristic out of that, then if you take plus minus 1 sigma from the mean, 68.2689492% of the components of the samples of the individuals which are part of that particular sample, or the elements of that particular sample, are within 68.2689492%. That is the distribution from the standard distribution. Statisticians have calculated and computed that. So that's the statistical number, which statistical distribution which would give you this percentage, which is the area covered under plus minus 1 sigma. So 68.27%, let us say, of components would lie between plus minus 1 sigma of any particular dimension which you measured. Okay, that is understood now. Now, we don't want only 68.26% to be within our tolerance. Therefore, we went on to the next level, which is plus minus 2 sigma. Plus minus 2 sigma says that 95.45% of the components, you can see the numbers in the slide here. There are numbers indicated there. 95.44% or 45% of the components or elements of, or what is the word for that? Elements, samples, or people, or whatever you are measuring, that particular item which you are measuring would be falling within plus minus 2 sigma. That means 95% of the components would have a variation between plus minus 2 sigma, and this plus minus 2 sigma is computable. So imagine, that's the magic of statistics. Really magical it is, isn't it? You measure 5 pieces, then find out what is the average of the sample, x bar, and find out the standard deviation of the sample, which is S. And then from there, you compute. There is again a formula to compute the population standard deviation, whereas the population central tendency, mu, will be the same as x bar. So there is no calculation required there. Whereas there is a conversion factor available to convert the sample standard deviation to the population standard deviation. Once you do that, you get the population standard deviation, which is sigma. Now you have got 2 numbers. That means, if suppose the diameter was 20, and you can say the standard deviation is 1. So you know that 20 plus minus 1, which is 19 to 21. If you say in that particular machine, whatever that is being, whichever machine it is, plus minus 20, 20 plus minus 1, which is 19 to 21, 68% of the parts will be between 19 to 21. Wow, miraculous, isn't it? And that's so simple it is. Then 95.44% of the parts will be between 18 and 22, which is 20 plus minus 2. Then 99.73% of the parts will be between 20 plus minus 3 sigma. That is 3, because our sigma is 1 there, right? So between 17 and 23, you would find 99.73%. So when the statistics historically evolved, the historians felt that 99.73% is a good enough topic for us to discuss. Therefore, they said, we will take that as the reference. That is the base for any calculation now. Any capability study is done based on plus minus 3 sigma. That's why at the bottom I've written down minus 3s and plus 3s. The plus minus 3 sigma is something which is extremely important for us to understand. So that is the standard. So whenever you talk about any population, any physical occurrence in this universe, you always calculate plus minus 3 sigma, and then these plus minus 3 sigma limits would be within, would be totally contributing to 99.73% of the population. That was way back, maybe 30 years back, 35 years back, when the statisticians thought that. And after that, as we evolved, we started talking about zero defect, and we can't really work with 99.73%. Now we said that, no, we want little more quality. So we can't accept that. Therefore, at some point of time, man said that, look, now we need to have plus minus 4 sigma. That means we need to have 99.993 or 994% of the parts within that plus minus 4 sigma. Therefore, I also always want to compare plus minus 4 sigma with my tolerance. Now comes the tolerance, or the new thing which I introduced, which is the LSL and the USL, lower specification limit and upper specification limit. What you do in statistics when you're doing a capability study is actually comparing the values plus minus 3 sigma to your tolerance. If plus minus 3 sigma is within 100% of the tolerance, then you would say that the capability index is 1. CP is what it is called as. CP is 1. If suppose plus minus 4 sigma is within the tolerance, then the CP becomes how much? 1.33. How is 1.33? Because always 3 sigma plus minus 3 is the standard. That is what somebody said long time back. So we have taken that as the base. Now 4 is what you have got, plus minus 4. So 4 divided by 3 becomes 1.33. So if you are talking about 1.33 of CP, that means you want plus minus 4 sigma within the tolerance, then it becomes 1.33 CP. Then comes the next one. Now, let us say sometimes that is also not sufficient. So we need to go to the next higher level, which is what we want to have plus minus 5 sigma within the tolerance limits, in which case you are talking about having 99.999,427% of the components or parts or occurrences in this universe within a particular limit, and that limit is plus minus 5 sigma. So if you're talking about having all these components within your tolerance limits, then you would have a capability of 1.67. How is 1.67 calculated? Where does it come from? 5 divided by 3. Do a calculation using your calculator, then you get 1.67. So simple it is. Now comes Motorola. We said no, 5 sigma is not sufficient for us. We need to go to 6 sigma, plus minus 6 sigma. That means we need to have almost zero defect. Why is it zero defect? Look at it. How many parts are beyond that? 99.9999998%. That means 0.000002% of the population would be beyond those values. That is plus minus 6 sigma. So when you have a process with plus minus 6 sigma within the tolerance limits, you would have a capability of CP of 2. So 6 sigma means CP of 2. Now you can ask me, how is it done that the sigma guys all tell that you need to have, you can have, when you have a 6 sigma process, you would have a DPMO, defects per million opportunities, of 34. Interesting question. I'm not showing that on the slide, but I'll answer you that question. In the case of 6 sigma, what happens? Like in this case, let us say this is the upper specification limit and the lower specification limit. There is a natural tendency of the process to drift between one point to the other point. It will never be in the one center always. Today morning it could be at the central tendency, and then later as the tool wears out, it could be coming to the right. Then after that, you change the new tool, it comes to the left, and then again it comes to the center. So there is a little amount of variation happening in the process, whatever be the process. To accommodate this process, the wise guys in Motorola said, when you are looking at a process, you need to be talking about allowing a variation of up to 1.5 sigma from the mean. 1.5 sigma this side, 1.5 sigma this side. This variation is something which is natural. We cannot avoid it. So if you have that variation, now you calculate what would be the percentage when you are talking about not 4 sigma, but 4.5 sigma it comes to. And that's where you get the number 34 defects per million opportunities. In which case, for a 6 sigma process, CP would be 2. Then there is another indicator which is equally important. That is what I'm going to introduce, and then come back to 3 sigma. There is what is called a CPK. CPK is what? Now, if you look at this particular graph, the central tendency is more closer towards the lower specification limit than the upper specification limit. Is it correct? Therefore, the risk of this process having higher defects would be more on the lower side. So you take the least between the upper specification limit and the lower specification limit, and based on that compute what would be the capability study, or what sigma would be within the tolerance limit, and then you calculate and compute what the capability of that particular process is. If you do that, considering the upper specification limit and the lower specification limit, where you are considering the drift between the two areas, like I said, then you get to an index called as CPK. So in the case of 6 sigma, the CPK would be 1.5 and the CP would be 2. And for the other processes, the index is called as CPK again. In this case, the pictorial which I have shown here, CP is also not 1, because 3 sigma is not within the tolerance at all. You see the upper specification and lower specification is closer than the process spread. Therefore, your sigma within the tolerance could be possibly 2 is what I would imagine, or 2.5, in which case the process capability here would be only 0.6 or something like that CP, and CPK will be even worse. CPK possibly is about 0.3, because if you see, majority of the components are outside the lower specification limit. Now here I purposely chose this picture of showing the distribution beyond the USL and LSL, because distribution is something which is natural, which is coming from the nature, whereas the specifications are something which we have decided, it's a man-made one. So you cannot really take the nature and then compress it to the man-made one. If you want to compress it, you need to have a new process. You need to have a going for a different technology. The process will behave the way it will behave. So you can only compare it with the tolerance limit and calculate the capability study. That is what the capability study is all about. Therefore, if you want to improve the quality, it's important to go in for a better process. And there's no point in doing more calculations. It doesn't really help. It's only numbers, like an accountant. This only gives you the numbers and the results are known and it's facts. Therefore, to improve the process, it's important to work on the process technology rather than the capability and numbers. So with that, today was quite exciting to me, very, very inspiring. Lot of statistical concept, made me remember my early 90s when I had introduced SBC in Brazil. And those days, of course, we would be happy if we had a CP of 1, whereas in today, 2020, a CP of 2 would be what is acceptable in the industry. So you can imagine the amount of progress that has happened. But at the same time, I want to say, unfortunately, though, there are a lot of companies who are still in the 90s, where you still have a CP of 1, but still they're feeling very happy for having had people at the end of the line sorting out the parts for good and bad parts and inspecting, rejecting, scrap. So it still continues in the world. It's not anything which is eliminated, but unfortunately, that is the reality. I'm sure we will all progress further and achieve overall a CP of 2, which is 6 Sigma. That would be magical. Then we will be having only 34 defects per million opportunities. So with that, thanks a lot for watching, and have a nice evening for those of you in India. Have a great day for those of you outside India, and for both, a very, very happy and prosperous new year, a healthy new year, and a safe new year 2021. Let it be the rebirth of a different kind of a world, different kind of a population, different kind of a society after the pandemic has gone by. And let's all pray for the best, and best wishes to you and to your loved ones, and see you tomorrow again, same time, with a different tool. So let me just give you a very brief peek into what is it that I'm going to be talking tomorrow. My tomorrow's topic would be on performance triangle. See, this week was quite interesting. Tuesday was about MBTI, which is nothing to do with technology or anything to do with numbers, rationale. Then came the Kaizen, which is a combination of rationale and mindset. And then statistics, capability studies, which is pure numbers and pure rational. There is no feelings or no sentiments, no emotions involved in that. And tomorrow I'm talking about performance triangle, which is a mix of both emotions and rationale. So see you tomorrow, more or less at the same time, 8:30. Maybe I get a little delayed. If I do that, please pardon me. And wish you all the best, and have a nice evening, and best wishes to the entry into the new year once again. And take care. Bye-bye.